Hello, this is Jack Jackson, and we're going to look today at using laws of limits and continuity theorems to help us evaluate some limits. So notice that the properties that we looked at, we called our laws of limits, had a hypothesis that the individual limits f and g must exist as real numbers, so L and M must be real numbers, not positive or negative infinity, or something else. They have to actually exist as real numbers. Now the C could either be infinity, minus infinity, or actually a real number. But the L and M, the limits, must actually be an actual limit. The proofs I gave included examples where C was a real number. In one case, I did one where C was infinity. But you can also modify the other proofs to show that they work for those values as well. Now, the main purpose for me, for my classes, is not that you should be able to reproduce all the proofs that you've seen in the videos preceding this. Instead, here's what you should be able to do. First of all, you should understand that formal definitions and proofs are important and necessary in order to be sure that results and techniques used are valid. So at some point you have to derive these results and make sure that they work no matter what before you can use them no matter what. You should memorize at least the basic epsilon delta definition of a limit of a function as x approaches a constant, because it's good to know the definitions. They're the foundation of what's going on in any subject, particularly in mathematics. And of course in mathematics, it's important that we be very precise about our definitions, because oftentimes just changing one word changes the meaning of the definition. Within this delta epsilon definition, you should be able to find an appropriate corresponding delta for any given specific value epsilon for a particular limit, so that the conditions in the definition are satisfied, or at least approximately find such a delta. You should be able to at least follow the proofs that were given. Now, not necessarily come up with the proofs on your own, or even be able to reproduce the proofs. That's not really what I'm after. But I'm after at least being able to follow what's going on when I go over the proof. And you should be able to see that this formal epsilon delta definition of a limit can be applied in some general settings, which lead to some general laws of limits, which in turn lead to even more laws of limits, which in turn lead to techniques that we can use to actually work some limit problems out, like we're going to do here in just a minute. You should definitely memorize the laws of limits, and they're pretty straightforward and intuitive, so there are no real surprises there. They do what you think they ought to do. And you should be able to use these to compute some limits algebraically. So remember, the laws of limits I'm talking about are things like this. The limit of the sum is the sum of the limits. Limit of a constant function is a constant times the limit of the function. Limit of the difference is limit of the differences. Limit of the product is the limit of the product limits. Limit of a reciprocal is the one over the reciprocal limits. Limit of the quotient is quotient of the limits, and so forth, provided that we don't ever divide by zero, and both of these original limits must actually exist. Now, let's look at some different techniques that we might use to actually help us work out some limits. Now, the first one is just direct substitution. Just substitute and simplify. Now, this is going to work if the function is continuous. So, of course, remember, a continuous function, the limit is the actual value of the function. So, in section 3 below, we're going to give a list of functions which we know are continuous, at least where they're defined, and others that are just continuous functions. And this list is actually going to include most of the functions we study in pre-calculus. So simple substitution is often a very good place to start. And even if the simple substitution does not work, it may kind of point out where the problem with simple substitution is, and then gives you an idea of where we might have a problem. For example, there might be some dividing by zero, and we have to do one of the other techniques to eliminate that dividing by zero. But oftentimes, a lot of the real well-behaved functions, we can just plug it in. So in this example here, we have the limit as x approaches 2 of 2x cubed minus 5x plus 1. Well, this is a polynomial function. Later on, we'll show that all polynomial functions are continuous. But I want you to actually look at some of the details here of how the limit laws are actually applied. So the limit of this sum is the sum of these limits, provided these individual limits exist. Then in the first and second one, we can pull the constant out front of the limit sign using that property number, I think it's number 2 above. Yes, property number 2. And the first one was property number 1. Now we can use the property of powers to say the limit of x to a power is the limit of x, then to the power. Then all we really need to know is that the function x is continuous, the function y equals x, so as x goes to 2, x goes to 2. So that approaches 2. So here and here, and the limit of a constant is that constant. So of course 1, 1, 1, 1, 1 doesn't ever change. The limit of that as x approaches anything is just 1. And so we get this right here. And of course if you look at that, that's exactly the same as just taking the original 1 and just plugging in the 2. And that works out to be 7, as you can see here. Okay, we can use a similar technique here. I didn't work out all the details, but the limit of the square root is the square root of the limits. Then the limit of the polynomial is steps like what we just did above. And so it turns out that you can just plug in the values here, and sure enough, this one works out very nicely and is continuous there. So in many cases, that works out just great. But of course, many times in calculus, we're not interested in those kinds of things where it's real well defined at the continuous places. We're often interested in what happens at the places where something else happens. Particularly, we're interested in a lot of the cases where we end up dividing by 0. That's kind of a very common thing to look at. So we need some other techniques that may work. One technique we can do is factor and cancel out, say for example, to simplify a rational function. So here we have a rational function in this example. When we take the limit as x goes to 5, if we try to just plug in 5, negative 5, you actually get 0 over 0 here. So you might check that out. Negative 5 squared is 25, plus 10 is 35. Negative 5 times 7 is negative 35. Add those, you get 0 in the denominator. So when we get a 0 in the denominator, we can't just use our limit rules up above, and it's certainly not a continuous function there because it's not even defined. So we need to apply some other algebraic technique. The technique we use here is to factor the numerator and the denominator. And in the numerator, we factor out a 2 with the distributive property, leaving us a 2 times an x squared minus 25. In the denominator, we use anti-FOIL factoring, where we break this down into the product of two binomials, x plus 5 and x plus 2. You can check that out to make sure that works. Use the distributive property in the top and FOIL, which is another way of saying the more complicated distributive property in the bottom. And x squared minus 25 is x squared minus 5 squared, so that factors as x plus 5 and x minus 5. Again, you can check that out by going back. Now, as long as x is not negative 5, you can cancel out these x plus 5s. Now, remember, x is not negative 5, it's only getting close to negative 5. So these two terms right here will cancel out, leaving you 2 times x minus 5 over x plus 2. Now, what we have left is continuous, so now we can actually just plug in the negative 5 here and here in place of x. And we no longer have 0 divided by 0. Up until this point, we had 0 divided by 0 if we try to plug in. But here we don't, so we can actually plug that in. You can see the rest of the arithmetic there. Negative 5 minus negative 5 is negative 10. Negative 5 plus 2 is negative 3. The two negatives cancel. 2 times 10 is 20. And the denominator is 3. So the limit is 20/3. Let's see if you can try this one here. Okay. The limit as x approaches 2 of 3x squared minus 4x minus 4 over x to the 4th minus 16. See if you can work this one out. Similar technique to what we just did. Go ahead and work it out on your own, and then come back to the video when you're done and you can check your work. Press pause now. Okay, now you've done this, hopefully, and let's check it out. So x to the 4th minus 16 is x squared squared minus 4 squared. So that factors as difference of two squares into our sum of difference pattern, x squared plus 4 times x squared minus 4. Then the numerator factors is 3x plus 2 times x minus 2, which is our anti-FOIL factoring. And the difference of two squares, x squared minus 4, factors is x plus 2 times x minus 2. Now, we knew if we just tried to plug in 2, we get 0 in the bottom and 0 in the top. So in the numerator and denominator both 0, you get a form 0 divided by 0. You know you got to do something else. That's an indeterminate form. we don't really have any clue what the limit might be. It could be anything. We've got to keep going and do some more work to figure this out. But it also tells you that x minus 2 should be one of your factors in the top and bottom here. And in fact, that's what we see. And in fact, they also cancel out here because x is not 2. It's only close to 2. So these are not 0. You can cancel them out. That leaves this fraction with here. That's right here. 3x plus 2 over x squared plus 4 times x plus 2. And now this one, you can actually plug in the 2 in place of x, and you can see it here. 3 times 2 is 6 plus 2 is 8. 2 squared is 4 plus 4 is 8. 2 plus 2 is 4 here. And so the 8's cancel, and you get 1/4 for the answer. All right, here's another one for you to try. This one looks a little bit more complicated. Compute the limit as h goes to 0 of 2 times x plus or x minus h. Yeah, that works. X minus h squared minus 3 times x minus h plus 1 minus 2x squared minus 3x plus 1 over h. Actually, I'd rather do this with a, well, it's fine. It's fine like it is. Now, like the last example, notice you put in h is 0, you get 0 on the bottom, but also you're going to get 0 on the top if you work this out. Okay, so it's this indeterminate form, 0, 0. We got to do something else. So see if you can expand this out, cancel out like terms, factor, cancel some more, get it down to something where you get rid of this h in the bottom. See if you can work on that one on your own, get it worked out, and then come back and check your work here in just a minute. Press pause now. Well, here's what we do. We're going to square this first. X minus h squared is x minus h times x minus h, which is x squared minus, that's wrong, x squared, this is minus 2hx plus h squared. So this was plus, this is minus, this is, that makes this minus, this one plus, minus, plus, minus, plus, minus, plus, minus. I think that's right. Let's take a look at that and see. Okay, let's see here. So, actually, what I really wanted to do? I really wanted this to be a plus. Let me fix that as a plus to begin with. Okay, so then what does that change here? That just makes all this plus here, and makes this positive here. Okay, so let's look at the steps again. Distribute the 2 now, so this makes 2x squared plus 4hx plus 2h squared. Distribute the negative 3, that's negative 3x plus 3h plus 1. Distribute the minus here, you get minus 2x squared plus 3x minus 1. Notice the minus 1, the 1 cancel. The 3x, the minus 3x cancel. The negative 2x squared and the 2x squared cancel. And it leaves this in the numerator. They all have an h. Factor that out. H is not 0, so we can cancel that. Now finally we don't have 0 divided by 0, so we can plug in x equals 0 and work that out. And so we get a limit of 4x minus 3.